Days ago that the scheduled speaker cannot make it, so I had to fill in. I would not then impress you too much because I didn't have much time to prepare this seminar. Part of it is sort of pedagogical and part of it is work in progress with Łukasz Turski. I will start with a very simple introduction, so I hope that everybody can learn something about classical relativistic mechanics. How do we do classical relativistic mechanics in textbooks? Say in Hamiltonian form, we write the canonical Hamiltonian equations. This is dH over dP, and P dot is equal minus H over R. Now the question is, what is H? And we know that in relativistic theory we have this famous square root.
And physically this particle moves under influence of what?
Wait and see. Let's take electromagnetic field, which is the best known example. Yes, so we have the famous square root. It must be relatively long because we need the minimal coupling, as it is called in quantum physics, P minus EA squared plus MC squared, and this must be multiplied by C. MC squared. Ooh, what? Postpone. Of course. And plus E scalar potential, and this is the relativistic theory of a single particle with mass m moving in an external electromagnetic field. This is scalar potential, E phi. Well, does it look relativistic? Because of the square root it does. Otherwise, however, we love to have mu and nu, and we love to have summation over mu. So the first question I will answer here is that there is a very cute formulation of relativistic classical mechanics which is completely equivalent to this one, which has all the indices appearing as they should. So now I can proceed with my prepared talk and show you how does this work. I have this device to change. And here's my stick. What is written here? Well, I begin with the phase space. Relativistic phase space should have 8 dimensions because we have 4 components of position and 4 components of momentum, which are equivalent according to special theory of relativity. So therefore, if I denote the positions psi and the momenta pi, the canonical Poisson bracket should read delta mu nu, where mu runs from 0 to 3. Well, we are really accustomed to something different. We say that time plays a different role. Here in this formulation, time plays exactly the same role as all remaining positions. So if this is true, then the general Poisson bracket will look like this one. And canonical commutation relations, which are written here in 3-dimensional form, now have a 4-dimensional form.
Of course, but then... Wait.
Everything will be clear. And I claim now that if I take my Hamiltonian in this relativistic form, which looks similar to this because there is a square root. However, here we have summation over all 4 indices. Moreover, we have the metric tensor here, which could in principle be dependent on the positions. And what is really surprising, it was certainly surprising to me, that the placement of the metric tensor here does it all. I get what I really want in not only in special relativistic theory, but also in general relativistic theory.
But it's not positive definition.
Of course not. This is the standard metric. It must be positive under the square root, otherwise the Hamiltonian is not real. And this will be, as you will see, guaranteed by the equations. So the equations, as I have written them here, are, and of course the general formula is using the Poisson bracket, that the time evolution, or let's say at this moment a parameter evolution, and in a moment we will see what this parameter is. There's no freedom here, it will come out. So I hope this part is clear. Everybody can write this down. If one remembers only the square root, everything else is just standard canonical theory. So what happens next? We have to write down these equations in an explicit form, which we'll do just differentiating. Notice what happens when I differentiate with respect to pi. Then I get, of course, pi minus a lambda in the numerator, and h drops down to the denominator. So here are the equations. d xi mu over d tau is equal, as I said, p in the numerator and h in the denominator, and the metric tensor here. Now the differentiation with respect to the position and time, of course, which is part of this position, is more involved, because in the square root, position appears in 2 places. It is appearing through the potential and through the metric tensor. So here are the equations. Now what I do, I just check the following. What happens to the square of the derivative, 4-dimensional? According to this equation, it is equal to c squared. So velocities are constrained on the basis of this equation. And here we see that tau is nothing else but the proper time. This is not something that I assumed at the beginning, but it comes out from this equation. So look at these equations. These are truly canonical momenta. There is a form of this set of equations that does not contain canonical but kinetic momenta. This is the kinetic momentum, which is, as you see, proportional to velocity, except for lowering the index. So this is the, and h in the, which is very important. Yes, absolutely. So now we proceed further, and what do we have? Well, first, h is the rest energy, because it's this square of kinetic momenta. Now, h is a constant of motion, because it commutes with itself according to a Poisson bracket. So I go up for a while back here, and if I eliminate the momenta here in the usual way, I differentiate twice psi. I differentiate then everything what is on the right-hand side. As I mentioned before, h does not depend on tau, so differentiation does not affect h. It affects only pi and a nu, which is important, because the derivatives of a mu will produce what I need, the electromagnetic tensor. And look, this innocent installation of g mu nu in the definition here does it all. It gives us the correct equations of motion in any geometry. Just this simple trick, which I found at the beginning rather amazing. They're just putting g mu nu of x, I get this. And now the question comes, what is the meaning of this h? Notice that in this, the left-hand side does not depend on h. This is the principle of equivalence. All particles move, no matter what is the rest mass, they move the same way. However, h enters here in the denominator divided by c squared. Now, what is the proper form here that we know from textbooks? The proper form here is that it's instead of h over c squared, there should be the mass of the particle. And here we have a theory of all kinds of masses, because depending on the initial conditions, the value of h is fixed. If I start with some initial conditions, I assign the values of psi and pi, and they produce some number with the right dimension for h. And this number is constant during the evolution. So this is a theory of all particles with all masses included in this one equation if h is as defined before. And this equation shows that the original scheme is completely equivalent modulo this one single problem that I have to fix my mass just by changing the initial conditions, nothing more. So this is the way one could introduce classical relativistic mechanics in textbooks. By the way, I don't have it in my transparencies. However, there is a neat way to quantize this whole problem. Namely, if I say at first blindly that I have the equations I, h, d tau, psi of tau, some abstract vector equals my h, our h. Ła. Rzeczywiście. Zaraz go. No, bo powiedziałem tylko, to widać, że na godzinę go odsunę, myślę, że skończę w tym czasie. Dobrze. If I just blindly follow Schrödinger and say if I have a Hamiltonian, I can write down my Schrödinger equation. Then we don't like square roots, of course, in the Hamiltonian. Dirac didn't like it, that is how he discovered his equation. But if I differentiate twice, just dt squared psi of tau, then on the right-hand side, remember h does not depend on tau, so we can only differentiate this.
Attention, a classical age, and what is
Wait, just a moment. If I differentiate twice, here I get the derivative here, so I need some, just to keep the dimensions right, I need h squared, and I will the square of I will produce times psi of tau. Now h squared now, according to the rules of quantum theory, momentum should be replaced by the derivatives, and I get sort of generalized Klein-Gordon equation. Why generalized? Because there is this additional parameter. If, however, h squared is nothing else but the part of d mu here, g mu nu, it even comes in the right position because this is the self-adjoint combination of the D'Alembertian. It acts on psi. And of course, electromagnetic. Yes, sure, it should be included, but I'm just showing what happens. If I now assume that my function psi is stationary in the tau parameter, that is, it depends on tau through the minus Im c squared tau, then I get the Klein-Gordon equation as I should. Why what?
Why it is stationary?
Oh,
If evolution, then evolution.
sure, this is like I am just considering. Yeah. This was a side remark which does not really have anything to do with the rest. I was just showing that one can even proceed within this framework to quantize this problem. Now let's go back here. And what can we do with this formulation? Well, we can be more ambitious, and this is what we are trying to do with Łukasz Turski, and to do something more. Oops. For some reason, must like it. Okay. So now I can go to kinetic theory. What is kinetic theory? It's a theory of many particles, which can be then described in terms of the density in the phase space. So if I have a discrete set of particles, n particles, I can write my density, which has now delta function like spikes, in 8-dimensional phase space. Completely unconstrained. Now, what does this integration mean? It means that if I look at a certain portion of phase space, I don't care when in proper time particles were present there. I don't care. Therefore, I integrate over all values of proper time just to get this density in a fixed volume. And this is what this function f means. Of course, since this formula is linear in the contribution from each particle, I can go to the smooth limit. Say I take so many particles that now I can describe it in terms of a continuous distribution in phase space. So here I have my f function, which is now a continuous function. There is even a better way of doing it, because I can express everything in terms of some initial data, and then I integrate over those initial data with some distribution of initial data. In this way, I will get rid of the delta function and get a distribution. This is like going from Lagrange picture to Euler and Lagrange.
Physically, it looks a bit dangerous to give initial value over the whole space-time.
Why? It works.
Normally, if we know what happens at a given instant of time, we should probably know the future.
No, no.
That is,
But
this function has a meaning. It's not a the confusion comes from assuming that this is like a distribution function in the normal kinetic.
That's right. It is not. It is not. It is not.
The density of the
But
word lines, and in some sense, we're talking about the Poincaré sets. We are asking how many trajectories cut the given part of a space, not caring at what was the proper time of
that's
this
right.
particle.
And you are free to assume f
Yeah,
value.
because we have this is an ensemble of the word lines, not the particle.
There's a very nice geometric object used here. This thing is densitized vector field.
facespace vector fields are exactly things we integrate over surfaces to see how many.
Yes, yeah, precisely. Anyway, this formula I may say is just a heuristic formula because I just wanted to explain what is the meaning of this distribution function. Now I can just say I do have a distribution function in this 8-dimensional phase space, and the question is, what is the equation that this distribution function must obey if these trajectories obey the...
But physically, the value of f given the space-time region, what does it?
It's a number of the world lines. But
That
we don't
cross-
know at what proper time the particle was
Yeah.
there. We see the world lines are objects, are really drawn objects.
That's right.
And we simply ask, okay, in that volume there is a certain number of world lines, but whether the particle is there at that moment I want to look at this thing, I don't care.
No, according to proper time we don't care, but time is fixed.
The real time, we
Yeah,
care,
of
but
course.
according to the particle.
Yeah, but I may forget about the proper time because there's a conventional parameter.
Yeah.
But what about real time?
Oh, it's a function of the real time. It's
Of x and p.
Okay.
One of the x's is time.
well,
So if I know the value of f on a given space-like surface, t equals 0, for instance, it does not.
yes, it does. No, look. This is the first. No. Of course it does. This is a first.
You will see it explicitly.
This is a first order equation in time, so you can write the derivative with respect to time on the left hand side and the rest on the right hand side, and you solve this. And you solve this first order partial differential equation using the method of characteristics, which will bring us back to trajectories, because this equation, as all equations of the first order, can be solved with the method of characteristics, which means that I can just solve this in terms of the trajectories, which was my starting point. Now, this equation looks gauge non-invariant, and it must be so because my canonical momenta are not gauge invariant. That is why we have a mu appearing here, and that is why we have this derivative. However, one can convert this to a gauge invariant form, paying a certain price. Namely, instead of parametrizing my f function in terms of p and x, I can parameterize it in terms of the kinetic momentum, x and k, where k is equal to p minus ea. What is the price that I will pay for this reparametrization? Well, k is not a canonical momentum. The components of k do not commute. But when I express my function f, I did not write it down here, I think, in terms of k, the equation becomes then gauge invariant, as it must, because canonical momentum is gauge invariant. Kinetic.
Kinetic momentum is gauge.
Can we see this equation?
I don't think I had time to. No. Now we go to the crucial part, which is work in progress, and we are fighting very hard to get something. Namely, the ambitious aim is to now, in a consistent way, couple gravity to this set of particles. How is it done? We take the Einstein equations with the tensor on. Oh, sorry. Yes, of course. It looks ugly.
Well, this is the work in progress.
Yeah.
R will be added at the proper time.
R. Next step will be adding. Something went wrong with my microphone, but I will fix it in a moment. So there is an R in our calculations, but we have not gotten very far with the calculations. Now, what is the energy tensor. Well, how do I get this tensor? How do we get this tensor? Well, from a variational principle. There is a variational principle for this classical set of trajectories, and the energy momentum tensor is obtained by differentiating the Lagrangian with respect to g mu nu. And this is what happens. H again drops down because, as you recall, H has g mu nu in the numerator. Therefore, if I differentiate with respect to g mu nu, H drops down. And of course, in the case when the mass is fixed, this would be just the mass of the
This is
particle.
kind of a dust, yeah?
It's more than dust. It's dust which does not have well-defined
No, there is no dust at all. So
No.
it is a set of
I think
particles
whether it's a
which creates the gravitation.
field, that's the difference.
This is the whole story.
Yeah, this is the self-consistent
Set
set of equations. So this is not dust because it produces gravitational field.
and the gravitation.
This I
It is
understand.
dust. It is
This
dust,
I
but
understand.
without the restriction that it has a well-defined velocity at each point. You can have, at each point you can have dust of arbitrary form.
This I understand.
This is not real dust, it's something very simple.
So this distribution function here,
It's not. This is a semantic. Whether
Yeah.
it's a real dust or not a real dust,
Yeah.
or not what we're talking about.
anyway, we have particles which do
It's a completely well-defined system. It's a
system of equations. However, it's not easy to solve. And this is, of course, the work in progress, because this equation must be solved together with Einstein equations, and g mu nu appears everywhere here. It must be the same g that appears in Einstein equations. So what did we try so far? Not getting too far. Namely, the simplest assumption, and that also should be written when we want to compare this theory with the standard kinetic theory. I don't have this slide, but I will explain this on the blackboard. Since H is a solution of this, one may say Vlasov of this equation, we can seek this solution for the function f of x and p in the following form. Delta function of h minus mc squared times some function constrained on the surface constrained by this delta. I will just say that this is xp, but of course this condition introduces some connection between the parameters. Now, if I substitute this formula into my equation for f, there will be a derivative of the delta function here, but it will be multiplied by the left-hand side of this equation acting on h, and this is 0 because h is a solution of this equation. And the remaining part is delta function in front and all the derivatives acting on x. Since my mass is fixed, I can eliminate p naught, the energy, and express it in terms of momenta and mass. And in this way, one can check that's an easy exercise. One obtains the standard kinetic equation with this constraint. However, the whole beauty here, because of some astrophysical or cosmological applications, is the possibility to treat all particles regardless of their mass, because we don't control the masses of the galaxies or stars. They are different. Therefore, this approach seems to be suited for astrophysical applications, because in normal matter around us, particles do have definite masses. But if we are talking about some large masses of various
universe,
or even not even on the scale of cosmology, but if we have say a disk around the star which also has particles of various masses, one could use this formalism. What are the difficulties and why we are struggling so much without great success here? Because there are various things that must be imposed to make this model sensible. One thing must be, look here, T is a functional of F. However, when the gravitational field ceases to exist, it becomes the Minkowski metric in the distant. If we want to describe some clump of matter, we assume that the space is flat, very far from this clump of matter. And that is a problem, because that means that when the metric becomes flat, T mu nu must vanish. And you can see that this is a non-trivial requirement, because F is positive, and this is not an easy task to make sure that even though F is positive, this will go to zero at large distances. Of course, one may try to solve some other problems disregarding this requirement that the metric is flat, some closed universe, for example, with matter inside, and various options here are possible. I have to admit that we didn't get so far, too far. What we tried is to guess some function f and see what happens. And the simplest guess, of course, which somehow, however, invalidates the generality of this approach, is to assume that f not only is a delta function in mass, but also that it is a delta function in energy, which is the simplest requirement one can introduce. If the metric no, that's all. Yeah, that's all. This is our answer with some constant here, which moves means how many particles. Okay, n, capital N, which says that a number here. Now, what are the problems? The problems are that one can write the f function and check that it satisfies the Vlasov equation. You may wonder, why does it satisfy, this part satisfies the Vlasov equation? Because it's a function of h. However, this is a function of p naught. However, if the metric here, we disregard the electromagnetic field, is the metric is not time dependent, then the derivative with respect to the time,
is a necessary
yeah, then the derivative with respect to p naught drops, and we can substitute any function of p that we want. And what happens then? Well, let me just point out what happens. Then the component t naught naught becomes quite simple. If we assume the metric in the form a dt squared minus b dx squared dy squared plus dz squared, the simplest metric which depends only on r.
And nothing depends on time.
Nothing depends on time. Then the metric tensor is equal, evaluated according to this formula that I mentioned, some constant which is not important, square root of 1 minus a divided by a. A is this here, so it's a relatively simple dependence on a. The left-hand side, of course, is known from textbooks. It's a differential expression built from a and b, and we can now solve these ordinary differential equations. However, the solutions are disappointing. I mean, when you plug this into Mathematica, you get exploding solutions. So far, this, as you see, automatically satisfies the requirement that far from this region where the matter is present, the tensor drops to 0, which is nice. However, how does this explosion occur? In almost all cases, A becomes bigger than 1. And at this point, Mathematica refuses to solve. I was trying to put absolute value here, but then absolute value in a differential equation is not something that Mathematica likes.
Human being causal that.
Pan Mikołaj. Coś.
Somebody who worked on this a few years ago. So the standard way to approach this is to first of all assume that the energy is always negative. And this typically means that the particles are trapped in a gravitational a potential that may not reach to infinity, and therefore this is really asymptotically flat. So you can indeed assume if your metric has symmetry, it also has conserved quantities in the equations of
Sure.
motions. You can in fact assume that this F depends just on this constant of motion. Energy is one of them, but you can also add angular momentum.
Aha, sure.
When it comes to dependence on energy, it's good to fix it, to fix a theta function there, which makes sure that the particles cannot escape to infinity. This way they're typically trapped spatially, and you get really asymptotically flat metric very easily. As for dependence on J, you have to use some kind of Gaussian or something like that.
Well, one way also to help to overcome these problems is to introduce the cosmological constant that will make sure that the right-hand side
Canonical distribution.
goes to 0. Yes, we also tried, but we have not gone too far to instead of delta functions introduce canonical. So then h will be in the exponent also, and it will play a role of some number of particles. We multiply by some mu, which plays the role of the chemical potential, and here we have an exponential, which is the temperature, and this is still work in progress. We'll see whether there are any solutions of these equations, which would be the ultimate.
Also trying to solve this equation in a brute form, for a linearized, for example, Russell equation, assuming that the G is given in a Poissonian approximation, and then you get a correction to the G's. The
Instability.
G's instability, and you get this
Newton Russell, which has also been studied quite a bit.
Okay, so that's the end of my story, and as I said, work is in progress. I hope that we will get somewhere. There must be some interesting solution obtained from this scheme, because there is a novel idea here to treat all particles regardless of their mass at the same time.